Hello everyone, this video is intended as mainly aimed at those people who are having to self-isolate so that you don't miss out too much, but also I guess you could use it as a revision opportunity if you're finding earthquakes a little bit confusing. So I'm not going to spend very long on anything, for which I apologise, but you can obviously ask me questions, and you should have access to this PowerPoint via the hazards folder on OneDrive. If you have deleted in fact, no, tell you what, I will just resend the link to the file on OneDrive so that you can access this PowerPoint and all of the hyperlinks and stuff in it as well. Right. I'm just starting off here. I'm not going to open any of these. These are all quite good websites, and there's a video clip there that will introduce you to earthquakes. They're just quite a nice sort of, settles you into the topic quite nicely. Okay, this is what you could use as a basis for your notes. All of this really is in the module booklet, but particularly if you wanted to create revision notes, or if you are just struggling with earthquakes generally, then if you use those as your headings, you won't go too far wrong. And I shall work through these, like I say, reasonably quickly, but just to try and give you a flavour of what we've done. Okay, so the definition of an earthquake is there. And if you were in class, the analogy I use is snapping a pencil, which you are very welcome to do if you feel like sacrificing some stationery. I think you would all agree that a pencil is a solid object, but if you apply pressure to either end of a pencil, so if you sort of try to bend it, it will bend. But it will only bend so far, and then all of a sudden it will split, it will crack. And that essentially is what an earthquake is. The Earth's crust is divided into plates, and those plates are moving. And as those plates are moving, they are subject to enormous pressures. And they will bend and they will adapt to that stress for a period of time, and they will get to the point where they cannot bend anymore, and they will suddenly move and jolt and snap, just like the pencil does. And I suppose the only thing for you to realise here is that the earthquake is the moment the stress is released. It's the sudden movement when all of that friction just gets overcome. And as I say, the pencil snap is the best analogy I can give you. Key terms, you need to know focus and epicenter, and you might be forgiven for wondering why the hell you're looking at ferrets and an elephant. It's because I had a student that just kept muddling them up, and so we were trying to think of a way that he wouldn't forget. And ferrets live underground, F for ferrets, F for focus, and elephants do not, E for elephants. E for external, E for Earth's crust. The focus is the exact point that the earthquake happens, or if you like the analogy, the exact point that the pencil snaps. That could be 300 kilometres down, 10 kilometres down, 50 kilometres down. It can be at a variety of depths. The epicentre is always the vertical point above it on the Earth's surface. So you just need to get those terms sorted. As it says there, the foci can be at very different depths. And all we know is that anything deeper than 70 kilometres, it has to be in a subduction zone. So that's when you have convergent margins, you have plates moving towards each other, in which a bit of oceanic crust is pushed down into the mantle. That's called a subduction zone, and anything deeper than 70 can only happen in a subduction zone. Just a little bit of extra knowledge for you. Humans can induce earthquakes, which means they can sort of encourage them to happen. And there are three ways. Dam building, purely because you add a huge amount of weight to the Earth's crust. And as the Earth's crust kind of shifts and adjusts to that enormous extra weight, you can trigger an earthquake. Weirdly, the opposite is also true. Mining removes a huge amount of weight from the Earth's surface. To give you a sense of just how big that mine is, that dumper truck is this dumper truck, well, or the same make anyway, and this is a human for scale. It just gives you a sense of how incredibly massive that is. if you remove that volume of material, the Earth's crust is going to shift and adapt to that, and that could well trigger an earthquake. Or, slightly more controversially, fracking. Now, the video explains what fracking is, and the news link tells you that we've had some very small, but nonetheless, we've had some earthquakes in the UK triggered by a process called fracking. So yes, humans can trigger earthquakes, but basically, mostly, they're caused by natural processes, and they happen at every single plate margin, okay? We don't get volcanoes at every single plate margin, but we do get earthquakes at all of them. We get them in subduction zones because of the friction between the plates. So as one plate is grinding past the other plate, you get lots of friction, and you can get an earthquake there. You can get them at a convergent margin between two continental plates. That's like the Himalayas, it's the mountain building one. And when you've got two great big lumps of rock colliding with each other, that's going to give you an earthquake. Divergent margins, this is one of the ones under the sea, a mid-ocean ridge. And what I need you to focus on are these blue lines. Divergent margins are not one long sort of gash in the Earth's surface where molten lava is pouring out. They're actually in little sections. And each of these sections is moving at a very slightly different speed. So when I explain conservative margins to you in a couple of minutes, each of these blue lines is like a mini San Andreas fault, okay? So it's the grinding of the pieces of rock moving at different speeds under the sea that gives you earthquakes here. No tsunami risk here though, because there's no vertical movement, and we'll talk about those in a bit. Rift valleys, where you've got a lump of continent being split apart by magma. So this is the divergent margin on land. As that continental crust gets ripped apart, you're going to get earthquakes. And conservative margins, you can have two plates moving past each other in opposite directions, or, as is the true case of the San Andreas, two plates moving past each other in the same direction but at different speeds, because it doesn't matter whether they're going the same way or opposite ways. If you've got little points of friction that are going to get stuck, they're still going to get stuck. And as I said, the transform faults on divergent margins under the sea are like very miniature versions of this. This is completely optional. It is in the module booklet as well. This just makes the thing I said about the pencil sound a bit more academic. The idea that solid objects will bend and then they get to a point where they cannot bend anymore and they break. So here we have some rocks in layers, probably sedimentary rocks in layers, and they all line up. Then they're subject to the huge forces of plate tectonics and they bend. And then the earthquake releases that pressure and the rocks no longer line up. There's a diagram of a fence in your module booklet, which is based on where elastic rebound theory was first discovered, which is a fence that was built across the San Andreas fault. Now, obviously, when the farmer built this fence, it did used to line up. You wouldn't build a fence like this. And then he noticed it bent, and then after a big earthquake, it no longer joined up, and he had to make this repair. So this is not compulsory. It makes a nice little diagram and is quite easy to show off a little bit of knowledge and understanding. But like I said, you can just cross it out and ignore it if you would rather. Right, earthquake waves. Now, if you were not in the lesson where I introduced you to one of my favourite geography teachers of all time, Keith Miller, please watch that YouTube. He explains P&S waves in a unique way, but P&S waves are really quite important. So when that person lands in a swimming pool, the waves that are generated are going to travel away from the site of impact in all directions. Okay, in the same way, when you have the release of pressure at the focus, you're going to get waves of energy travelling in all directions, and Keith will tell you lots. But what you fundamentally need to know is that there are two types, P waves and S waves. The module booklet tells you everything you need to know, really. This is a very short summary. P waves are called primary waves because they get there first, and the reason they get there first is they're faster. That's pretty obvious, isn't it? They can travel through anything, as Keith will demonstrate in his very unique way, and they are compressional, so the direction of movement is kind of backwards and forwards. S waves, there's lots of alliteration here, if you like a bit of alliteration. They're secondary, they're slower, they're solids only, they're shear waves, lots of S words. So try to learn the differences between those, only in that level of detail, but as I said, it is in your module booklet. And then we don't need to get bogged down too much in the detail of this, but you just need a passing understanding of shadow zones. Now, P waves, and please watch the Keith Miller video if you haven't already, P waves can travel through all parts of the Earth. But when they get to the liquid outer core, they are refracted. So you can see they change speed and direction here. Because of that refraction in the liquid outer core, you get two parts of the Earth's surface that do not get any P waves. S waves cannot go through liquid. It is impossible for them to go through liquid. So they stop here and here. And the brilliant, clever thing about these shadow zones is what seismologists are now able to do is they can find out which parts of the world experienced the earthquake, which parts of the world didn't, and obviously it's one of the ways of working out where your earthquake actually happened. The other beauty of P and S waves is that is how we know that there must be a liquid outer core, because if there wasn't, then the S waves could travel through it. So yeah, don't get too bogged down in shadow zones, just acknowledging their existence is enough for us in geography. There's a few websites there that might help you, and then time for one of my terrible diagrams. I think I did a better job on the board in class, but for those of you self-isolating, I thought I'd better have a go. I do apologise. P waves are compressional. The direction of movement is backwards and forwards. S waves are side to side. Oh, there's another S word, side to side. So the waves that we are most interested in as geographers are surface waves, because surface waves are the ones that make buildings fall over and kill people. And in geography, that's the bit that we're actually most interested in. So people are like, where do surface waves come from? What's that all about? Well, actually, they are the surface expression of P and S waves. If you've got a compressional wave like this, when it reaches the surface, it's going to make everything go up and down. And when you get a wave like this, when it reaches the surface, everything's going to go from side to side. So surface waves are not some kind of weird, different sort of a wave. They are the surface expression of the P and S waves. But they only have enough energy, just going to go back, near the epicenter to do damage. Okay, so just think about constructive and destructive waves in coasts. We've said if you had a storm in the English Channel, it would create massive waves because the waves are created by that storm and then they hit the coast. If you had a storm down off the coast of Argentina, it would generate waves, and those waves would be quite big on the coast of Argentina. But as those waves travel the whole length of the Atlantic to reach, say, Cornwall, they are going to lose energy, and by the time they hit the Cornish coast, they're going to be pretty pathetic. And that's where our constructive waves come from. The waves that you experience, even on a day where it's not windy, where you are. Okay, so you'll always get waves. In that same kind of way, the further the waves travel, they lose energy. So by the time your P and S waves get the other side of the planet, they will be picked up by seismographs. They're not going to be noticed by anything else. But here, if your focus was, 10 kilometres down, then the waves have only got to travel 10 kilometres until they reach the surface. That is going to be a lot of energy, a lot of shaking, and a lot of damage. So you only get surface waves that can do damage near the epicenter, which is why it needs a special name, because that's the bit that's going to be badly affected. That clip will sum up quite a lot of what I've just told you, and it will also give you a sneak peek of where we're going. It's really good. It's only 6 minutes long. It's Ian Stewart. Please watch it. It's really good. Then, there is an awful lot more information in the module booklet than you need about measuring earthquakes. So I'm going to try and make it really clear. You need to pick either seismometer or seismograph. Now in the real world, those things mean slightly different things, but for Geography A level, they're not that bothered. Don't tell the geologists, but they're not. So pick a word, seismometer or seismograph, and just know that that's how earthquakes are measured. And if you want a little bit more information about how they work, I've put a YouTube there. But essentially, if the ground moves, this pen, it used to be a pen on paper, it's now an electronic pen, but this pen will make a mark and then you can measure it. So that's literally it. You just need to know the name, seismometer or seismograph. And then there is some stuff in the module, and those of you in class, I've got you to write the words, "This is optional," at the top of the page. Everything from knowing the name of seismometer or seismograph up until the Richter scale is really important. Everything between those two is like, it's there for your interest, you can cross it out, you don't have to care. All right, so this is a bit of a seismogram, the readout from a seismometer. Okay, background noise. The earth will always be moving a little bit, lorries driving past, whatever. It's never going to be a flat line, but you will recognise when your earthquakes arrive. Okay, so your P wave, they arrive first, remember. So P waves come first and your S waves are second, and they come second. The most important bit of information on this is the PS time interval. So you need to calculate from here to here how long it took from the first P wave to the first S wave. Or rather, you don't, seismologists do, but that's what they do. They find out that time. Then these have been created from decades worth of earthquake data. These just exist, these graphs. So you have to find out what your P and S wave time gap was. Okay, so you use a graph like this. And then you come down on here. So sorry, there's your P and your S wave. There's your gap. Then you come down to the x-axis and you're like, oh, so we were, oh, I don't know, let's make it up, 9,200 kilometres away from the focus. So by using that and that, you can work out how far away you were. Now that's not necessarily particularly helpful, because there are going to be lots of places that are 9,200 kilometres away from the focus. As long as 3 seismographs picked it up, what you do is you get your good old compass out, ladies and gents. You draw your radius from the measurements that you just got, and where those 3 circles overlap, that's where your earthquake was. So it's very clever, isn't it? So you need your graph, you need a compass and a map. So that's where you work out where the earthquake actually happened. Then for magnitude, it's very clever again. This is an actual readout. You need your PS wave time interval. This time you need to measure the size of the single biggest wave. Okay, so whichever was the biggest wave, you have to measure the amplitude. And then these have been dreamt up by much cleverer people than me. And what you do is you plot a mark on here where the SP time interval was. You plot on here what the amplitude of your biggest wave was. You get your ruler out and you join those 2 points together, and that is the magnitude of your earthquake. Okay, now let me just remind you, all of that was entirely optional That was the last compulsory thing, knowing the name of the equipment that measures it. That is the next compulsory thing. All of what I just said here is for interest. If you can talk about it, great, but it's not direct, it's not on the syllabus, it's just there for interest, and maybe as a show-off opportunity if it becomes relevant. Okay, there are two ways of measuring earthquakes. I'm not going to say very much here because it's in the module. You have to know about the Richter scale, and the most important thing that you need to know is that it is logarithmic. That is mentioned in your module booklet, and if it doesn't make any sense, please can you Google it, okay? That's the most important thing that you can know about it, because you will hear people like on the news and in the general public saying sentences like, this earthquake was a magnitude 6.4 and this magnitude was a 6.8. So they were very similar earthquakes, and it's like, oh my God, no. Because the logarithmic scale is such that there is a big difference even between decimal places. And if you were to write sentences like that in an essay, it's just not going to end particularly well for you. You won't fail, it's just, you know, it's going to count against you. So please make sure that you understand that the Richter scale is logarithmic, but it is our favourite scale. It's widely used, it's very well respected, it's brilliant, all right, it's good, it's quantitative, it's objective, it's good. There is this other pathetic scale, which I'm very rude about generally, called the Mercalli scale. You need to know it exists, you need to know it's a load of rubbish, okay? It's subjective. So this is based on a period of time when there weren't that many seismometers around the world. And therefore, if you couldn't measure it on a seismometer, that was tricky. It's based on people's experiences and the amount of damage done. Now, you know what people are like. Some people exaggerate, some people downplay, some people embellish. If you ask 10 people their experience of the same event, you'll get 10 slightly different stories. Relying on people's experiences is not great. And damage, that's better, but can you compare the amount of damage done in a typical less economically developed country to a more developed country? No, because building quality is different. Could you compare the amount of damage in a Victorian house to a modern house? No, building standards were completely different. So it exists, but it's just a load of tosh, really. Effects. Now, people know all about these. I am not going to say very much because some of them are fairly self-explanatory, and there are lots of YouTube clips that you could use within this. I can't show you them on this video because I've discovered when I play a YouTube within a YouTube, I get all sorts of, it's not necessarily a very good idea. So you'll need to open those yourself. I'm going to go through these really quite quickly. Aftershocks. Aftershocks are earthquakes. Therefore, they do all the same damage as an earthquake. And actually, they can be slightly worse because if everything was damaged in the first earthquake, these just make it worse and worse and worse and worse, okay? Aftershocks are earthquakes. They're just smaller earthquakes, and they can be equally damaging. Mass movement. You have to know about mass movement for coasts. So the good news is that when you revise mass movement, you can do it for 2 modules. In coasts, it happens because the waves are attacking the bottom of your cliff, and that encourages everything above to kind of collapse. This happens because the ground shakes. If you had anything loose on a hillside, the shaking by the earthquake will encourage it to fall down. Don't get too much into flows. Earthquakes do not cause flows. That's associated more with hurricanes and things. But they do cause rock falls, landslides, and to a certain extent slumps. Okay, so there's some video clips that you can watch and things like that there. So revise that. Liquefaction is weird, and I've put loads of YouTube clips there because they are all equally good but very, very different. Liquefaction is when a seemingly solid substance turns into a liquid. It's weird, you need to watch the YouTube clips. But it will only happen on what's called an unconsolidated sediment, which means if you have built your house on granite, it is not going to turn into liquid. Like, no, that's not going to happen. With proper planning and proper geological surveys, you can avoid building houses on unconsolidated sediment, and therefore you're not going to have too many risks from liquefaction. It is an effect of earthquakes, but only in very certain places. However, the bottom two clips, you will see the devastating effects of liquefaction in Indonesia, where maybe that level of planning is not quite so possible. And that's basically what happens. The shaking means that the solid grains no longer touch each other, they're separated by water, and of course once they're separated by water, everything behaves as a liquid, which is why it's called liquefaction. And yeah, it's a problem. Building collapse. If tsunamis are not involved, which of course they're not always, the main cause of death from an earthquake usually is building collapse. And we have a saying in A-level geography, earthquakes don't kill people, buildings do. It is generally the main cause of death. Quite often a big, more developed, less developed country difference in that. And then tsunamis. There are some questions on page 57, and there's an article which gives you all the answers. So it'd be really useful for you to have a read of that article. It's really good on tsunamis. And then I've included some footage, and there's that. You don't have to watch this slide. I would highly recommend you watch those three. You don't have to watch those, it's up to you. Depends how bored you are in self-isolation. If you're really desperate for things to do, yeah, watch it, be really helpful. But the first clip on there, the top one, just reminds you that you only get tsunamis in convergent margins where you have subduction, because what you need to trigger a tsunami is you need a vertical movement, and it's only in those subduction zones that you get that. So please make sure you do a bit of revision on that. Okay. Finally, right, if you are faced with anything dangerous, could be coronavirus, it could be a wet floor, it could be an angry bull, doesn't really matter, anything dangerous, then you have 4 options, all right? Move away, do nothing, modify the hazard, modify vulnerability. And we've been through this with volcanoes. Move away. Yes, for individuals or families. Can everybody on the planet move away from earthquakes and volcanoes? Not a chance. So that is just not possible. Do nothing is the stupid approach. That, is not going to end well. Modify the hazard. Not really. So we said this for volcanoes. Can you stop volcanoes erupting? No. We had a couple of examples where you can spray lava with water, and that worked. And they put some degassing columns in Lake Nyos, and that worked. But basically it wasn't an option. Well, ditto. You can, to a certain extent, manage mass movement by bolting hillsides together, by draining them, by covering them in nets, so if there is a rockfall, hopefully the net catches the rock, by putting these little platforms in, so if you get mass movement here, the people driving along this road hopefully will be safe. You can manage mass movement, but that's it. You can't stop earthquakes. So, as with volcanoes, we are left with the 4th option, which is we know earthquakes are going to happen, but we're going to try to make sure that when earthquakes happen, people are not injured or killed by them. Modify vulnerability. And we have fewer options than we had for volcanoes. Volcanoes, if you monitor your volcano, it will tell you probably when it's going to erupt. It will have warning signs. You predict that, you evacuate people, you save lives. Death tolls from volcanic eruptions are going down. Unfortunately, we cannot predict earthquakes, and we'll pick up on this after half term. I'm going to show you a DVD, if I can find it. I can't find it at the moment, called Why Can't We Predict Earthquakes? And no, it's not on YouTube, I've looked. Anyway, why can't we predict earthquakes is fab, and it just says we've given up, essentially. We know where, if you've got the money to map them. We don't know when, we don't know how big. They've spent millions of dollars and thousands of hours, and I think we're just getting to the point where it's like, no, we can't predict earthquakes. So all you can do is educate people on what to do when an earthquake happens, and try to make sure that if buildings are often the main cause of death, well, why don't we build buildings that are much less likely to fall over? Now, I've put various clips there. This one is a television advert that is shown on New Zealand television every 3 weeks-ish to remind people. This is something you can do now. This is, depending on when you're watching this, Thursday the 15th of October. You can join in with the Great Shakeout if you want to. If you're really bored in lockdown, well, sorry, not lockdown, in self-isolation, you could join in with the annual practice that they have in California. There's kids' cartoons, there's a bit of a documentary, etc. The best thing to do, exactly the same reason that we do fire drills in the UK, you educate people so that you save lives if an earthquake happens, okay? Get your emergency kit ready, and then try to make sure that when an earthquake happens, that the buildings are not going to land on everybody's head. Now, this diagram's in your module booklet. You don't need the detail, but what you could write down is that making a building earthquake resistant, I'd much rather you use that phrase than earthquake proof. I don't think we should ever describe anything as earthquake proof. But making a building earthquake resistant adds about 10% to the cost. Not a problem in more developed countries. Could be a deal breaker in less developed, couldn't it? However, we've got such good engineering in the world now, we can build skyscrapers that are earthquake resistant. You can name drop this one if you want. This is Taipei 101 in a highly active earthquake zone. And essentially it has a massive shock absorber. This is the kind of thing that a car has, so that when the wheels go over lots of bumps, you don't feel them quite as much as the wheel does. And they have this enormous thing in the middle of the skyscraper, and that basically absorbs the earthquake and the building's fine. Isn't that clever? Or if you want a different one, if you don't like Taipei 101, there's Torre Mayor in Mexico, which has these enormous cross braces, and that it works in the same basic principle. They absorb the movement of the earthquake and the building stays up. And that's how we manage earthquakes. Tsunamis, we have warning systems. Everywhere has got them. The Boxing Day tsunami, which some of you might decide to do as a case study, was a bit of a game changer for this. Pre-2004, I think the Atlantic and the Pacific had tsunami warning systems, but nowhere else does. They're now everywhere, essentially, and you just tell people to run uphill. It's the basic fact. Get yourself to higher ground as quickly as you can. And yeah, so that's what we do. And we're going to pick up on that after half term. I know that was a bit quick, for which I apologise, but that might at least give you a bit of a clue as to what you're doing for earthquakes. Hope you're all right in self-isolation, those of you that are, and if you're revising, hope you're fine too.